Hello, everyone. Good evening. Quick intro. I'm Mirathar, Performance Engineer, Cloud Infrastructure Engineering, Netflix. My co-host, Amit Arora, Principal Solution Architect, AI ML AWS. In today's talk, we'll explore how Netflix evaluate AWS instances, primarily focused on AWS accelerated compute. For example, NVIDIA GPUs and the AWS Silicon Premium instances. We'll explore how Netflix CI/CD platform and the benchmarking framework is used by the Netflix services to validate AWS instances for their respective workloads. We'll talk at a high level LLM models, popular inference engine frameworks, and the serving techniques that are used for optimizing model execution and deploying into production for scalability. We will dive deeper into the AWS foundation model benchmarking tool called FM Bench. We'll discuss its features and capabilities and how Netflix used the tool to validate LLM inference performance across AWS instances, ensuring that performance meets the scalability, latency, and throughput requirement for the ever-increasing number of Gen AI workloads. I hope all of you are Netflix subscribers. Great, yeah. That means that you know that Netflix streaming service is famous for its recommendation and personalization. These services are fueled by machine learning algorithms that are used extensively to recommend relevant titles to our global subscribers that is now approaching 300 million paid subscribers. Everything on the members' homepage is an evidence-driven, A/B tested experience that we roll out and backed by the machine learning models. The demand for accelerated computing at Netflix continues to grow due to the transformative potential of Gen AI. At Netflix, that means building custom, pre-trained and fine-tuned models and deploying scalable AI-enabled services. Our Copilot platform is instrumental in enabling model exploration, allowing developers to experiment and innovate with Gen AI-powered services. Some notable Gen AI projects at Netflix that is deployed or in the process of deploying are text-to-image generation, conversational-based search, real-time adaptive recommendations, and the React-based search use cases. These initiatives aim to make subscriber and customer interaction more intuitive and meaningful. It also highlights the need for a robust AI-first infrastructure that is capable of meeting the growing computational demand of the future Gen AI workloads. At Netflix, we evaluate AWS instances using industry standard benchmark as well as production load. Canary and squeeze testing integrated into Netflix CI/CD platform and automated test harness help us with these automation. As part of right-sizing the Gen AI workload, we begin by determining the service accuracy, latency, and throughput requirements. We then iterate over various foundation models, AWS instance sizes or types, and the service stack. For example, NVIDIA Triton, TensorRT, TGI, VLLM, etc., to identify the combination that delivers the best performance and scalability. That ensures that the workload meets SLO requirements while staying within the allocated cost and the budget. This automated approach of right-sizing the workload empowers Netflix owners or the service owners to make data-driven decisions on deployment cost, capacity requirements, and optimizing pre-scaling and auto-scaling targets. All these efforts ensure that Netflix service deliver optimal performance even during popular, live, or on-demand events, providing a rich and seamless experience for our global audience. When benchmarking foundation model, several components include the model parameter, quantization, and service stack play an important role. Model parameters such as weights and activation represent neural network learned knowledge and thus important for ensuring accuracy in large language models. Tokenizers and embedding together enable contextual and deeper understanding of the user prompt and efficient text generation when working with LLMs. During inference, model parameters and activation must be stored in GPU memory for a quick inference, and thus places a significant demand on GPU resources like KV cache and the compute and the low latency memory, all these things. One can optimize compute and memory requirement or memory usage by quantization techniques, for example, like mixed precision or low precision, like FP8, int8, and int4, even int1 is available. But it's all really dependent on the accuracy requirement of your workload. So we'll talk also inference engines that are used for optimizing the execution of the model, like TensorRT or VLLM, and they are mainly used to improve mainly used for optimizing the access to the hardware and to improve the utilization. Also, the inference servers that act as a layer in between the customer request and the inference engine. These are just intermediary between the user request and the engine, and they are used for managing the GPU resources. They have tens of features. For example, tensor parallelism. They have concurrent batching, and then also the LLM-based optimization, like flash and the page attention type of features. And the common popular frameworks like Triton, DJL, TGI that can be used.
Thank you, Amir. So welcome everyone. Foundation model benchmarking, can you hear me now? Foundation model benchmarking tool, or FM Bench, plays a key role in helping Netflix benchmark and right-size generative AI workloads for price performance. FMBench is an open source package. It can be used for benchmarking any foundation model on any AWS generative AI service. It can be downloaded from PyPy and also from GitHub. The QR code that you see on your screen would take you right to the FMBench repository. It is model agnostic and AWS service agnostic, which means you can take any foundation model available on, let's say, Hugging Face, the Meta Llama 3 models or the Mistral models. You can take any proprietary model that you may have fine-tuned yourself, or you may take the third-party models such as the Anthropic Claude series of models available on Bedrock. You can benchmark all of these models using FMBench in exactly the same way. You can have these models deployed on a platform of choice, whether it is the Amazon EC2, including the Amazon Trainium and Inferentia instances. Through FMBench, you can have these models deployed and benchmarked on Amazon SageMaker or consume them directly from Amazon Bedrock. FMBench provides a unified configuration file for testing out all different combinations. So Amir just walked us through everything that is involved in LLM benchmarking, whether it is the inference servers, whether it is the inference engines, whether it is the different instance types that are available. FMBench provides a unified configuration file in which you can express all of these and test for all of these combinations. And finally, once the test is run, FMBench provides several metrics for evaluating price performance, and not just metrics, it creates a detailed report, which we will see shortly in the next few slides, which allow you to make business decisions for your workloads. Now, these metrics include things like inference latency, time to first token, time to last tokens, transaction throughput, how many requests can I serve per minute, what is my token throughput, and so on and so forth. All of that is put in a cohesive report that you can then consume. We'll see an example of such a report in the subsequent slides.
AWS FMBench tool is feature-rich and stands out well among other competing Gen AI inference benchmarking tools that we have tested. Key feature worth highlighting are the support for a Long Beach prompt dataset that is specifically designed for a task requiring extended token sequences, and that ensure consistencies across public and the private models. It also has extensive customization options like batch sizes, latency targets, prompt sizes, and you can have set up for various concurrency requests for the tailored evaluation. It supports a comprehensive set of inference engines and inference server that we discussed to ensure flexibility and to test various execution and deployment scenarios. It also offers granular, detailed LLM GPU server metrics paired with the built-in analytics reports that help you to get deeper insight to make data-driven decisions. So this is one of the examples of the various reports and charts that it generates. The goal is here to identify the price performance of two instances types. We want to get the cost estimate of 10,000 requests that meets the latency budget of 2 seconds. In this case, we are comparing the latency of the prompt size of 3,000 to 3840 range. I mean, there are different sizes of prompts available that you can analyze depending on your workload requirement. But a larger prompt size tends to have a higher latency at various concurrency level. Larger bubbles indicate more transaction per second. That means better throughput. So one can easily conclude from that the P4D with NVIDIA A100 provides superior price performance, considering it offers low latency and a higher throughput at a much lower cost. And it's as compared to the G6E48XL with L40S that is significantly lower throughput but at a higher price point. The performance delta that you see is due to the availability of HBM and the GPU to GPU NVLink, and that makes a big difference when you are doing LLM inference with the tensor parallelism enabled.
So these slides over here, the charts that you see on the left side or your right side is an auto-generated report from FM Bench. It walks you through a list of tables and numbers and plots which you can use for interpreting the results of a test. It also includes accuracy numbers. We use an LLM as a judge to evaluate the accuracy of the model. So a very comprehensive report that is auto-generated for you. We didn't want to create a data analytics project out of all the metrics that these tests generate, so it's done for you. And one of these charts here describes the performance of a particular open source model, the Llama 2 13B, on different instance types, and sees which instance types and serving stack option provide me the meet my cost constraints as well as my latency constraints. So these charts are all generated and we can make business decisions out of it. And this chart here, it's also generated by FM Bench. It really gets to the heart of the business problem. So the problem that we want to understand is, for my given workload, how many instances of which instance type would I need to deploy so that I can serve, let's say, 1,000 requests per minute? Do I deploy it on a G5X large? Do I deploy it on a P4D, which is very powerful but more expensive? Or I go all the way to a P5? This chart would say, for example, if I want to deploy up to 100, serve up to 100 requests, maybe I can do that by deploying 2 G5X large instances. But if I go to 1,000 instances, I may have to deploy 20 G5 2X large, but only a single P4D. If I go to 10,000 requests per second, I may end up deploying about 200 G5 2X large instances, but maybe only 3 P5 instances. So those kind of considerations you are now able to make by visualizations included in the report. These are interactive charts, so you can mouse over it and it will tell you, well, I needed these many instances of this particular instance type, and this is what it would cost. So it becomes very easy to answer the original business question that for my workload, what is the right serving stack, both from a latency and a cost point of view.
So this is the internal benchmark that we executed. This is not the comparison type of benchmark. It's really help you to understand how to size your application and match it to the instance type. For example, in the first column, the P4D is the right instance when the latency is the concern. And for a workload like real-time LLM inference, this is a right instance type. However, if the cost per transaction is the concern, then the Trainium, the Trainium instance will be a better option. G6 instances fits well where mid-level price performance is the need. Remember that B6E offered in 1 GPU, 4 GPU, and 8 GPU configuration, and it is as compared to the A100 that only comes in the 8 GPU configuration. And then also the CPU instances that can be fit into GenAI workload environment where the batch type of a workload needed. For example, the document embedding for the RAG use cases, where latency is much more relaxed. Also, the Netflix uses TROF, which is the unused cloud capacity, to pre-compute the subscriber recommendations, and that's how you can able to utilize thousands and thousands of CPUs that are sitting idle and can able to do the batch type of a inference on it for kind of free. Okay. So also their hybrid setup is available where CPU and can be used for the pre-processing and the inference run on GPUs.
So how can you get started with FM Bench for your benchmarking need? It's really simple. We've created a companion repository for FM Bench called the FM Bench Orchestrator, which makes this process really easier. There is a video that you can look at. There is an FM Bench website which guides you through all the details of how to install FM Bench, how to configure it, and how to run it and interpret these reports. Finally, FM Bench is an open source project, so any requests you have, please feel free to create issues on GitHub and or reach out to me on LinkedIn, and we will take care of those requests. Going forward, we are also adding agentic workflows evaluations into FM Bench. Thank you very much for your time, and we'll be hanging around for any questions.
Thank you.